So before we discuss how caches are implemented, I first wanted to cover what kind of problems we are trying to solve using these kind of devices. So what are caches? Well, as you may recall from the crash course, there was some number of problems that needed to be solved in order to make a computer run fast. One of the problems was that there is a mismatch between how fast we execute instructions in the pipeline and how quickly you can access memory. So typically you can complete an instruction every cycle, which is a fraction of a nanosecond, while the DRAM is a fairly slow device and it may require, for example, 200 cycles to read and write from memory. So there's a big mismatch, and that's where caches come to play. So here's a picture where the cache sits in between the pipeline and the slow memory. And the name of the game is to make sure that the pipeline can access data from the cache and not from the memory with a very high likelihood, and also to make sure that that access is fast. So typically, as you see here, you would like to have in the order of a cycle or a couple of cycles of access time. Actually, the problem that caches is solving is much more general than that. We have a very deep, what's called memory hierarchy today, as well as in the past in computers. So we have the disk with the huge capacity, but they are very slow, maybe 5 milliseconds. We have the DRAM that may take 100 nanoseconds to access, but the ALU that performs the operations can operate maybe at a third of a nanosecond to perform an operation. So an ALU can read and write data from a register with about a third of a nanosecond. There may be some small chunk of fast memory called static RAM, SRAM for short, that it may access in maybe a nanosecond. And also on the same chip, maybe there is some larger SRAM that it can access in 10 nanoseconds. So if the memory hierarchy is this complex and this non-uniform, how can we manage this as a programmer? And this hierarchy is, if anything, we are seeing more and more levels added to this hierarchy. So solid state devices, SSD, for example, is something that's sort of from an access point of view sits in between DRAM and disk. How can we deal with this fairly complex structure in a simple way? Well, back in the good old days, it was complicated. We actually asked the programmer to explicitly move data between the different levels in the hierarchy. So for example, a programmer could say, I would like to move a block of data from disk to a specific place in DRAM, and then later on say, I would like to move some subset of that data into a much faster SRAM, and then at the end of the day, the program had to write everything back to disk. So the problem with this, well, of course, it's very complex to ask the programmer to do this, but part of the problem is also portability. What happens if you run the same program on a machine with half as much memory or twice as much memory? Then you have to rewrite the program. And also multitasking. If you run several programs at the same time, and all those programs explicitly move data in and out of specific address locations, then they may start to step on each other's toes. So instead, what we have today is an implicitly managed memory hierarchy where the programmer he actually doesn't need to know anything about this memory hierarchy. The data will automatically, by magic, be moved to the right level in the cache hierarchy. So in some sense, the programmer will believe that it has all the data at its fingertips, while what actually is going on is lots of movements of data in the hierarchy. So the movement of data is automatic. During this course, we are going to talk about a couple of ways the programmer can help or improve the efficiency of the memory hierarchy by giving hints to where the data should reside or should not reside, but more about that in a couple of videos. Not that long ago, 1995, we had another kind of hierarchy, and that was the hierarchy of information you needed when you wanted to place a telephone call. So for example, if you wanted to call somebody in your province, so in Dalarna, it's where I grew up, you could find the telephone number in a telephone directory, maybe in 30 seconds. You could call the number service to get the telephone number for somebody in Sweden, and if you wanted to call somebody outside of Sweden, that was a big problem. I don't even know how long time that may take. So in order to speed up this process, typically I had a little note next to your telephone where you wrote up your most recently accessed telephone numbers. So you see the same kind of memory hierarchy as in the previous example, where maybe you had 100 people on your note, maybe you had 20,000 people in your telephone directory in your bookshelf, 8 million people in Sweden and 6 billion in the world. So it was incredibly important, to speed up your work. It was incredibly important to find the telephone number you looked for on your note. These notes were typically organized as an address book, and your parents probably are still using some of these address books. So caching in the context of the memory hierarchy works very much like the kind of address books we had in the good old days. So the address book has what's called an index function to quickly find the page where the data that you're looking for, the telephone number, resides. And this index function is typically the first letter of somebody's name, typically the first letter of somebody's last name. On that page, you will have tuples of information. One is an address tag that uniquely identifies what item for which we store the data. And then you have the data itself, so the telephone number in this case. So if you have a telephone book like this, where you can only write a single name on each page, we have what's called a direct mapped cache with 28 entries if you use the Swedish alphabet. It's a direct mapped cache, which means that there is only one place where each piece of information may reside. So you don't have to search this page, you use the index function, and you can directly determine by looking at the single entry here if the telephone number you're looking for resides there or not. So this is, of course, the way it works. You take the first letter of somebody's name as an index function, and actually, since you know that whatever information is on this page here ought to start with the letter T, you don't need to write the first letters. You can save yourself some ink here. You just write Omi here if you want to store Tommy's telephone number. When you do a lookup, you compare the part of the identifier that you didn't use as the index function. You compare that to the address tag that's stored in the address book, and if they're equal, you're happy, and you can use the data that comes out of the telephone book, the telephone number. If there is a miss, let's say you're looking for Tuomas telephone number, index to the same page, and then you determine that Omi is not equal to Omas, then you will have to go and look up the telephone number in the telephone directory or call an operator and so on. And once you got the new number, you may decide that Tuomas, it is more likely that you're going to call Tuomas in the future. So you're going to update your address book to store Omas number and write it in there. Question we should, and this, of course, this index function and these address books that we've used for centuries. However, we should actually ask ourselves if this is a good indexing function. So typically we use the first letter of somebody's last name. And I would claim that this is probably one of the most stupid index functions you can use. There are a couple of reasons for that. One is that, at least in Sweden, it's very unlikely that somebody's last name will start, for example, with the letter Z compared with somebody starting with the letter A. And since we use an index function that is more likely to contain the letter A than the letter Z, we're not going to use our pages in our address book in a very smart way. The other reason is that the first letter of somebody's name is not very uniformly distributed. For example, my last name is Hagersten, starting with an H. That means that the page, the letter H, the page H in my address book is completely full with all my relatives. So it's really hard for me to fit anything there. While, you know, for you in this class, you're depending on what letter your last name starts with, you may clutter up some other page. So anyhow, this index function here, it's not used in a very uniform way, which means that we're not going to use the storage resource in the address book in a good way. So let's keep that in mind when we design caches later on. So we're going to now turn to how to design these caches. So caches is a small memory that sits in between the CPU and the slow and boring memory. And before you start to do a lookup in the slow memory, you start to do a lookup in the address in the cache. So you provide, as an input to the cache, you provide an address of the data you would like to look at, and the cache will give back to you the data, the word typically, as well as a signal, which is a hit signal telling you if you can trust the word that the cache is giving back to you. If the hit signal is not asserted, that means that you cannot use the data returned from the cache, and that's the point in time when you have to go out to the slow and boring memory, bring in the data, and possibly update the cache, so next time you access that piece of data, it will be in the cache instead of in the slow memory. So this is what we use caches for in this course, but and the way these caches are organized looks very much like the address book that I talked about before. We're going to have to quickly find the data we're looking for. We're going to have some kind of index function to get to a just subset of data that we may be interested in. If it's the direct map cache, we can just quickly determine if the data is there. Slightly more complex caches, we may have to do some searching on this page as well before we determine if the data is there or not. So this way of implementing caches is typical for hardware implementations, but cache knowledge can be useful in many different areas as well. So, for example, when you design a new computer, you have to understand how to design caches, and that sort of has been my profession. But it's also very important to understand caches when you would like to write an optimized program, as you will see later on in this course, or when you write a compiler, or even when you write an operating system. So sometimes you need to understand caching behavior to get correct behavior for operating systems as well as for programs. It's also important these days to understand how to implement caches in software. So we have web caches, disk caches, file systems, and so on. They are examples of caches. And some of the tricks and techniques that we'll learn in this course can also be applicable when you would like to implement those kind of caches.